Good afternoon and welcome to Granollers. We all know that there are drivers, maybe several of us, especially during our teenage years, who love the loud sound of the motorcycles or the cars. Why do some people want their cars to be loud? Does it give them a thrill, or do they want to show off? It's hard to understand why some individuals love having a vehicle that alerts the whole neighborhood to its presence wherever it goes. What can we do in the cities? Do we need more police officers? Is it possible to automatically control noise in large open spaces? What is the legal threshold in real traffic conditions? How do we measure it? We will hear about experiences with noise radars and prototypes from our panelists joining us from around Europe. And to them, we give them our warmest welcome and sincere appreciation. To the participants, who I will introduce now in the same order of appearance in the session. From England, here with us, representing Intelligent Instruments, now here, help me to welcome Mr. Reuben Peckham. You can join us on stage, yeah. From Switzerland, connected online, we welcome the head of the acoustic group of the École Polytechnique Fédérale de Lausanne, Dr. Hervé Lissek, and also, hello. And also from Switzerland, the co-founder and CEO of Secureaxis, Glenn Meleder, who I think is online as well as the Professor Lissek. We also, from Spain, to talk about a test that has been done here in Granollers, we welcome Mr. Anton Gomar, co-owner of Control for Environment. Hello, hi. And also from Spain, and the head of operations and consultancy of Opus Remote Sensing Europe, and also is the technical leader of the European project Nemo, Noise and Emissions Monitoring and Radical Mitigation, Javier Buigas, who will explain trials of devices in Rotterdam and Barcelona. Thank you. Finally, we welcome from France, joining us online, representing Brit Paris, Mr. David Bernfeld, and also from France. I'm not quite sure if they are connected yet, but yes, okay. So, Mr. David Bernfeld from Brut Paris, hello. And also from France, the inventor of the Medus technology and the Hydra noise radar prototype, Mr. Christophe Mietlecki. Hello, good morning.
Hello.
Well, let's start with the prototype presentations and experiences with the noise camera from Intelligent Instruments that Mr. Reuben Peckham, who is going to tell us about it. Thanks. The floor is yours.
Okay.
You have your mic.
Thank you for welcoming me here, and thank you for listening to me in English as well, which helps me enormously. So, slides. How do we change? Yeah. Okay. Thank you. Okay, so I'm an engineer, an acoustic engineer, based in Southampton in England. If you don't know Southampton, it's about an hour south of London. So we're 24 Acoustics. We're a practice of acoustic consultants. We've been established since about 2004, and there's about 15 of us. And we undertake work across the entire built infrastructure. A few years ago, we had a particular need to, or we had an opportunity to develop our own noise monitor, which we called an intelligent noise monitor. And from that, a new company was born, which is called Intelligent Instruments. And now we design and manufacture a range of special instrumentation, so noise, vibration, dust monitors, nuisance monitors, and of course, acoustic cameras, which is what I'm here to talk to you about today. Oh, I'm sorry, I didn't press the button. Okay. So the development of our monitoring system started in 2004 we had a opportunity to develop a system that measures amplitude modulation from wind turbines, wind farms in real time. Some of you may be aware there was an algorithm that was developed a few years ago which we were instrumental in writing. And we had an opportunity to build a system that measures that in real time, helps wind turbine and wind farm operators to overcome issues of excess amplitude modulation very quickly. From that, the system merged into a multi-channel system that measures noise, vibration and dust, and we use it in our own work significantly in construction and demolition sites. And then in 2019, we were approached by the Royal Borough of Kensington and Chelsea. That's a borough in London. It's a very, very wealthy borough. It's probably the wealthiest borough in London. And they have a particular issue with noise from supercars. So people that drive Ferraris, Lamborghinis, whatever, up and down residential streets at 3 o'clock in the morning, keeping everyone awake. So they were looking for a system that would measure that, quantify it, and look at a way of policing it and potentially fining these people. So we adapted our existing system. We fitted cameras to it, changed the software, changed the firmware, and in the autumn of 2020, we tested 2 systems in London for them for a period of 3 months. In that time, they issued 150 fines, and they were very pleased with the outcome, and they have since purchased 5 systems themselves, which are there permanently, and another council in London, Westminster Council, have purchased another 2. So at the time of speaking, we have 7 permanent systems policing the streets of London, and we have another 2 going in actually in May. So by the end of May, there will be 9 noise camera systems in London. And the 7 that are there at the moment are basically issuing about 50 fines a month. So in terms of the technology, it's relatively simple. 2 high-resolution cameras. One looks up the road, one looks down the road. Class 1 accuracy, so it's a precision microphone and preamplifier system, processor, 4G modem, and obviously some algorithms and some code in there. The way it works is it records video, audio, and noise level continuously. And it triggers. If it detects noise from vehicles, it triggers. And when it triggers, it saves a portion of that data, uploads it to the cloud, and the user can view it and act on it remotely through a web interface. So in the UK, I have to say, I don't know what the laws are in Europe, but in the UK, there are no statutory noise limits. There's no objective noise limits for road vehicles. So everything is assessed on a subjective basis. So our system is a little bit like a police officer or a local authority environmental health officer standing on a street corner listening and making his own view. Is that car being driven aggressively? Does it have a modified exhaust? Is the noise it's producing excessive? And fines are issued through local authority legislation, which is called the Nuisance Vehicle Public Space Protection Order System, which I'll talk to you in a minute about. And our system basically allows a remote subjective assessment. It quantifies noise level as well, so the user listens back to and watches the video and the audio, sees the noise level, and they make a judgment. So it requires a user interface to do that. And from that, they make a decision as to whether they fine or not. Okay, so I have a couple of examples. So these are some video screenshots from the back end of our system. Hopefully this is going to work, and hopefully you'll be able to hear this. Okay, I'm no supercar expert, but I think that was a Lamborghini. And then I think, it needs some help. It's not going on to the next slide, no. It's just playing it. Well, you can listen to it again, but it needs to go on to the next slide. Yeah. Oh, there we go. Okay, right, here we go. Yeah. Okay, and a motorbike. I've been told that we're out of time, so I'm not going to bore you with the legislative details, although obviously if anyone wants to talk to me about that afterwards, they're more than welcome to. I'll just quickly tell you about our experience. So we have, from our monitors in London and the prototype systems that we've tested elsewhere, we've got a database of 35,000 events, range of different locations, urban, rural, different cities, different road types, different vehicle types. The system's simple, but it's Class 1 precision accuracy, and it's robust, and we think it's cost effective because of that. The London authorities are serving 8 to 10 fines a month, so it's probably paying for itself. And then just very finally, an interesting fact. So this is some data that's come back from Kensington and Chelsea. And I was going to ask you to guess which cars are the worst offenders, but we don't have time. But here you go. So this is 5 cameras over the period of a year. So BMW are the worst, or have been the worst, but surprisingly Lamborghini is number 2. Okay, thank you very much. Okay.
Thank you, and
No
sorry.
problem. That's all right, no problem at all. No problem.
So we're going to try to be on time for each of us, just to have time to go through all the different cases. And I really appreciate, Reuben, that you just stick to your slot time. Thank you. Okay, then we want to hear now the experience of the Swiss project NORA, Noise Radar, from Dr. Lissek, head of the acoustic group in the École Polytechnique Fédérale de Lausanne. And
hello? Can you hear me?
Yeah.
Yeah.
Yeah. If you share your presentation, you please.
It's already shared, so it should be available. Yeah.
Great.
So, yeah.
Thank you. Mm-hmm.
So Shai, thank you for invitation. So I will briefly speak of the Noise Radar project, which is a Swiss-funded project by InnoSuisse, which is the innovation instrument of Switzerland, and this is a collaboration between Secureaxis, a startup company in Geneva, EPFL, so École Polytechnique Fédérale de Lausanne in Lausanne, EPIA, which is a Geneva engineering school, and also Canton de Genève with the service, so the SABRA, which is the, sorry, can you see? Yeah, the Geneva Canton Service on Air, Noise, and Non-Ionizing Radiation. So this is a project based on the technology that already exists, developed by Secureaxis, which is called AirTexT, which is consisting on doing a passive detection of vehicle noise that allows counting the traffic, categorize the vehicles, also estimate traffic flow and speed of cars, and monitor the overall sound pressure level emitted by road traffic at the position of the radar. And this tool has been already deployed in many cities like Geneva, Zurich, Basel, Hamburg, Paris, to cite a few. So if you see on the picture here, this is mainly consisting of a box that comprises 2 microphones that we don't see in this picture, sorry, but they are inline microphones that are able to track and detect the position of the cars. And we have also a class 2 microphone that is attached to the box to be able to measure the sound pressure level, the global sound pressure level. And this is mainly an educational tool. So you see that we have some warnings to the people that are making too much noise. And this is based on, so this is based on estimation of the angle of arrival of the sound and capturing in the same time the picture of the car passing by. So the objective of NORA project, which is ongoing, so we haven't much progress to show, but this is mainly the objective, is not only to be able to detect and track and monitor the vehicle and also take pictures, but the idea is also to be able to automatically process vehicle categorization according to the Swiss law called Swiss 10 Plus categories, which is basically categories of different cars that can be light or trucks, and including some electric vehicles, according to this description in the bottom right part of the slide. So this is made with artificial intelligence and signal analysis. Another objective is also to be able to track and to measure individual vehicle noise level, which is a bit tricky, as we will see afterwards. And additionally, we estimate that it would be also good to be able to assess vehicle noise annoyance based on psychoacoustic metrics. So we need to define those metrics based on psychoacoustic study. So this is one of the objectives of the project. And the second objective, which is in line with what we have seen before, is to be also able to address anomalous driving attitude, because in the Swiss law, we have so this is a French speaking, a French version of this Swiss law, which is about the rules regarding driving habits. And there is some articles that refer to the law regarding the fact that people are not allowed to make unnecessary noise. So there are some subjective way to assess that, but it's written in the law, and we can make the system able to track those anomalous driving attitude. And also one other aspect, which is also in line with what we have seen, is to be able to identify anomalous engine or exhaust system, so artificial fake engine exhaust. And another features of this project is that this radar is planned to be deployed in network. So we have a whole infrastructure that combine edge to cloud platform IoT in order to communicate between each radar and to be able to adapt to the environment, to be aware of the context. I won't speak of that because this is not my specialty, but you need to know that there is this network part of the project. So basically what we do is we identify time delay of arrival. So we use 2 microphones or many microphones, and with each pair of microphone, we are able to identify the exact position, so the angular position of a car in real time, thanks to a signal processing technique that is called general cross correlation, that allows to find the delay between the 2 signals arriving at the 2 microphones in real time. So this is based on a PhD thesis published 10 years ago already by Patrick Mamaoli, which showed the applicability of this to traffic monitoring. And basically, when you have a car passing by with a 2 microphone, the cross correlation allows us to to identify in real time the exact angular position. So the time delay of arrival is related to the delay between the 2 microphones, which is also related to the angle of arrival of the car. So when it passes by, here there is no delay, and then you have some phase lag and phase lead depending on the position of the car. We are also able to identify or to measure the speed of the car by just measuring the slope of this curve. So we have many features that are able to be derived from this. So yes, this is basically what we do for each time frame. So let's say 100 milliseconds of time frame, we're able to process this cross correlation and stack them together and have a time series of cross correlation that gives you this kind of curve. And you see that you're able to see clearly the S or Z shape of these curves, and you are able to estimate the speed by measuring the slope, but also the size of the car by measuring the distance between the 2 curves here at the position where they pass by near to the microphones. The second part is to be able to categorize sound. So here we will rely on signal processing on the spectrogram, so the time frequency maps. So here you see a series of timestamps or spectrogram stamps of different cars passing by. So this is the x-axis is the time, the y-axis is the frequency, or a nonlinear version of the frequency, which is called the Mel scale, and the color map is the sound pressure level, if you want. And you see that depending on the car and the car driving attitude, you have different shapes, and we think that we're able to derive some identification of a specific car category based on this image recognitions. So since many cars are distinguishable by hearing, we think that the machine can be able to do the same with signal processing. And the machine learning part is based on the fact that the noise, different noise can be compared to prototypes, and that if we train well a neural network, we are able also to identify this noise compared to some prototypes, thanks to machine learning techniques. So this is the goal of this part of the project. We have also the goal to evaluate sound pressure level, but it's a bit more tricky. So first we need to have class 1 or 2 microphone to have standardized sound pressure level estimation. We need to be able to estimate the distance of the sound source to the antenna, so to estimate the R, so the distance from the car to the microphone, to be able to backpropagate this to a standard distance like 7.5 meters as in the ISO standard. But the problem is that if you have multiple sound, competitive sound, it's almost impossible to distinguish the different car, and there is no mean without using beamforming. So the problem is that with our technique, it's a bit difficult to achieve this sound pressure level estimation. So there might be some challenges to solve. So just to finish on that, the challenge that we need to solve is basically mainly on the individual noise level estimation. So first, we need to be able to certify the microphone antenna as class 1 or 2, which is a bit tricky when you have a bulk antenna. So it's very easy when you have a single microphone, a standard microphone. But if you multiply this microphone like 4 to 8 microphone, it's very difficult to have this certification. We have also difficulties to distinguish the multiple cars that are competitive with only a few microphones, and the distance estimation is not accessible with our signal processing techniques. As regard the categorization of car noise and anomalous car noise identification, we need to develop multiple robust metrics based on spectrum, harmonicity, time modulation, attack. So this is also work in progress, but we begin to have a good result, and we think that we are on the good track. And as regard machine learning, so we need to learn. So we need to feed the database with some data. So we need to process thousands of samples, which is a bit tricky. And the problem also is that this technique is a bit black box, and we have difficulty to get some physical feedback on what it will achieve. So yeah, these are the challenges that we are trying to tackle in the coming year. Thank you.
Dr. Lissek. Thanks. Now is the turn to hear two different experiences from Spain. We'd like to hear first a very low-cost pilot experience developed here in Granollers, the refitting of existing transit cameras into acoustic radars that have developed Control for Enviro and Key Acoustics Engineering. And Anton Goma, co-owner of Control for Enviro, will explain to us. Anton?
Good afternoon. Yes. This is Anton Goma from Control for Enviro. We are a company providing AI services, AI algorithms. And for this project, we have worked together with Key Acoustics, who couldn't come here today. Well, I'm going to explain it on behalf of them too. And also on behalf of the environment service from the Granollers City Council, who had the idea of this low-cost and acoustic radar. We understand for acoustic radar, we focus just on the detection and identification of noisy vehicles, just that. The system is working since last January. Pardon, it could be nice to you to see that. This is the one, yes, moment. Moment. Marta, I think there is something. Yes, this is the one. Okay. Yes, it's working since January. And the budget was 6,000 euros plus taxes, development included. So it's a really low-cost solution. After a first design phase, we prepared the sonometer. The camera is, as the title says, it existed already there. So this is focused for already existing traffic cameras. And then, of course, we had to add also a process unit and with which we could get pairs of license plates plus noise level. This results, it's what we are going to introduce today to you. This image shows how the local regulation states that a vehicle here has to be measured in order to determine if it's noisy, too noisy, or it is not. So in this case, it's a little bit different as you explain it. They want very specific points of measure. They are thinking of a closed room with in an environment completely controlled. And if in these conditions, they can say, yes, this is a noisy vehicle, hence it can define it, or it is not. And I want to make you clear which was the approach of the Environment Service in the Granollers City Council. They wanted an alternative way to solve that, because we assumed that it's very difficult to transpose those measuring conditions up to a lamppost in the street in a non-controlled environment. You see that the technology is there to do incredible things, as you or the lecturer before has told us. But in our case, we were looking for something much more simple. So we knew that we couldn't do that, but what we pretend is to find the noisiest vehicles in town. And that's important, in town. So not everywhere. And in town, we can count with a certain recurrency. So more or less, they are going to be always the same, those who are noisy. And that's the point of this. What we pretend to have is a list of the noisiest plate numbers, so that we can call them for a technical inspection. So this is not an automatic finer, let's say. It is just a way to send people, to send cars to technical inspection. Actually, in Spain, it's not possible to fine, even for exceeding speed, automatically. There always has to be a policeman, an agent, someone qualified for fining. So what we want is to have an indication, some not accurate enough measures that, thanks to a very simple big data analysis, can be complemented till the moment that they provide us that list that we want, that list of noisiest vehicles. By the way, here I put that the current maximum threshold from the local and most of noise regulations in Spain is 91 dBAs for those vehicles on the move. And this level, this threshold, we translate it to 75 dBAs at the distance that we have put our sensor, more or less about 3 meters. So this is it. You can see there in the up part, in the top part of the image, the Sonometer. We installed a very simple, commercial, affordable, and widely used sonometer by CSVA. The microphone of this sonometer is even omnidirectional, so you see it's what's there. And we also provided and installed an image processing unit, which is placed in the town hall data center. Both share the same infrastructure, power and communications. And of course, then there is a software analysis for synchronizing the image with the sound level, and which is really to do other analysis thanks to AI. We can not only know which are those vehicles, the plate number recognition, but also we can have an idea of what kind of vehicle is that just by AI classification. The experience took place in a two-lane, one-direction street in the business industrial area here in Granollers. We chose a place not particularly noisy. And we detected 146, in these 3 months, we detected 146,000 transits produced by 66 different vehicles. Okay? This is our, let's say, universe. And to better understand that, this is the example of one of those vehicles that usually drives below the acoustic radar, and for 17 times, which are the, you can see that the sound level exceeds the threshold of 75 dBAs. So this is an example of vehicle that could be asked for technical inspection. And taking that 75 dBA threshold as reference, in general, we found 17,000 transits exceeding it, and the most important of our results. These 17,000 noisy transits were produced by just 205 different vehicles. So again, that principle of the very few are responsible for most of noise, which applies not only to noise, but we could apply it to many things in a room, in a classroom, or in politics even. So just 205 recurring noisy vehicles, the 0.3% of all the vehicles identified, were responsible for the problem. So meaning that this is really a feasible way to take care, to approach to that problem. And well, that's all. That finally we have a list. This is an example of the list. Of course, this list of the noisiest vehicles will be longer or shorter depending on the threshold. And not only that, at this here we said that we want 5 repetitions minimum for a vehicle to be called for technical inspection. And now the challenge with this, which is really easy to solve, is not to lose any noisy vehicle first, and second, not to send any silent vehicle to technical inspection. That's all. So thank you very much for your attention. And
thank you. We will need to talk to police officers about this, about those 200 vehicles that are noisy here in Granollers, I think. Thanks, Anton. The second speaker from Spain will show us the experience in Rotterdam and Barcelona, even though I think Barcelona we won't have any results yet. And as part of Nemo's project, funded by European Commission, with more than 11 countries involved, and the goals now go further. Now you measure not only noise, but also gaseous emissions. And we have the pleasure of having here on stage Javier Boigas, Head of Operations and Consultancy of Opus Remote Sensing Europe and Technical Leader of the European Project Nemo. Thanks.
I'll stay here. Okay. Thank you, Marta. I don't know if I have to put the presentation. Okay. That's it. Okay, thank you very much. So I'm going to speak. There are a lot of coincidences with my previous speakers, so that's really nice. I think we are all going into the same direction. I'm from Opus Remote Sensing Europe. We are mostly focused on the remote measurement of vehicle exhaust emissions. But today we're going to talk about the remote sensing of noise and tailpipe emissions together. So first, just a glimpse about regulation. This has been commented. So there is a need for enforcement. So here, the City Council of Granollers, the City Council of Barcelona, which is here, that we did a recent pilot. there is a clear need to target those, as was commented, maybe top 1% or top 0.5% of the noisiest vehicles circulating among us. No? But this is complex. There is no, at least in Spain, there is no regulation about this. In most of the European countries, there is no regulation at all. There are different legal options that we can take. There can be national regulations based on type approval limits, but this is complex because type approval limits are defined in very specific conditions at the laboratory. We can then use these systems only, as was commented, as an alert system, so that vehicles that are the noisiest then are sent for a roadside inspection, and the police put a microphone on the close to the tailpipe and check if that vehicle is noisy or not. But then there can be some local regulations. Happy to hear the example of Kensington, where, yeah, indeed, if there is a clear disturbance, a clear vehicle that is noisy, the police has the power to go and find that vehicle. But local regulations must need to be put in place. So what is the H2020 Nemo project? It's a very, very ambitious project, very complex project that touches a lot of things. 18 partners from 11 different countries. We have 7 demo sites across Europe. And the most important part of the project is that sentence above. Nemo will create and test a completely new remote sensing technology that can measure both noise and gaseous emissions from individual road vehicles and trains in real time. So there are 3 major blocks of developments that we are doing in the project: vehicle sensing, integration, mitigation. The integration part is interesting, is important. It is about physical integration, like integrating the microphones on the streets, or, as was commented before, using existing cameras on our cities. But there is also a virtual integration, like integrating this data in other data platforms, communicating to the infrastructure, and even the synchronization between different sensors on the site. But now I'm going to talk about vehicle sensing. So there is 2 types, exhaust emission sensing and noise sensing. And in the project, we are developing solutions both for road traffic, railway traffic, and sea traffic. So let's talk about road traffic. What is the Nemo remote sensing system? This is an schematic, an overall view. We're basically talking about a system for the automatic and remote analysis of each vehicle's emissions in free-flow circulation. The system is able to measure for each vehicle that passes by its tailpipe emissions, so CO, NO, NO2, particulate matter. Then also the speed and acceleration. I will talk why this is important, very important. Then, of course, the vehicle noise signature. We measure ambient conditions, of course, such as temperature, humidity, if it's raining or not, things like this. And also we capture the license plate of that vehicle. So all of this has to happen in less than 1 second, and all has to be integrated and processed for analysis. So the noise sensing solution is led by our partner Müller BBM, that maybe some of you here know them. They're from Germany, very, very good guys. They have developed a solution that I think has similar of the algorithms and the mathematics that have shown my previous speakers. So with vehicle separation algorithm, peak level corrections, the system is able to do a source localization and distance measurement so that we can pinpoint and isolate and provide a unique noise of a vehicle in a free flow streaming. So what are the experiences in Rotterdam and in Barcelona? In Rotterdam, Müller BBM deployed this microphone array from October 2021 to March 2022. 24/7 operation. We had 260,000 pass-bys events. 80% of the vehicles were passenger cars, and here you can see some of the, I think I had, maybe I passed it. Yeah, this is an example of the Rotterdam setup. So the technology itself of the microphones is not complex. It can be mounted on a pole or on an existing semaphore or whatever. Here, 4 microphones were deployed, a license plate camera, a speed radar, and also a system for meteo, and wind measurements. So what is interesting about what we are developing and what was tested already in Rotterdam? Something very important that was already commented, the difference between a noisy vehicle and a noisy driving. So we saw that example in London, with the Lamborghini. That was clearly a noisy driving style. So that guy wanted to show off. He clearly made a driving behavior to be louder. And we have to separate what are the typical noise of the vehicles, what noise is from the vehicle itself or the vehicle characteristics or a vehicle driving style. So that's why we are measuring both the speed and acceleration, so that we can also filter the data and do analytics based on those 2 factors. Here in Spain, fast acceleration is not forbidden. So we have speed limits, but not acceleration limits. So it's difficult to enforce or regulate the noisy, if a vehicle is too noisy because it was accelerating too fast, or how do we regulate this? It's difficult. So working a little bit on the Rotterdam data, you can already see that we could establish some limits, like, okay, these are normal noisy vehicles, these are medium noisy vehicles, and these are the highest. We can call them high emitters in noise. Some vehicles are 15 to 20 decibels louder than, let's say, similar vehicles driving under similar conditions of speed and acceleration. That's the interesting part. We can compare if there is a fault in the vehicle, for example, or if it's from vehicle driving style, etc. Curiously, in Rotterdam, because of the site and because of the fleet, there are not many motorcycles in Rotterdam. Okay, it's not like here in Barcelona, possibly in Granollers. So most of the noisy vehicles are passenger cars, maybe also in Kensington. And one interesting thing from this is learned that probably one single measurement is not enough. We need, as also was exposed before in the Granollers example, repeated measurements of a vehicle so that we are sure we don't have a false positive. We are absolutely sure that this vehicle is constantly overexpressing some noise levels. And here you can see an example of a Ford Mustang. The license plate is just from Google, so it's not a real car. That was 3 times in that 1 top % of the noisiest vehicle. So clearly, this vehicle could be sanctioned. Now in Barcelona, we did a test a few weeks ago. That's why, Marta, we still don't have results, because this was done before Easter. And it was the first time, actually, that we also deployed together the noise and the exhaust remote sensing devices together. And here, we evaluated more centric and complex locations. The location, the environment, is also important, because if there are closed buildings, the trees, if it's an open space, a canyon type of site, this all is complex for the measurement and to say if a vehicle is noisy or not. And here we measured also in more centric types sites. So it was a very short pilot, 5 days of measurements in 3 different sites of Barcelona city center. But we captured more than 12,000 unique vehicles. Now we have to analyze this data and see what we'll get. Here, some examples. So we just used very laboratory type, and so in let's say instrumentation. So you can see that all the equipment is there without their casing. We have some enclosures for the system, but here we are working fast. And here, a couple of 2 more examples in city levels. You can see that the buildings are really, really close by. And what is next? Well, first, we will analyze Barcelona data. Let's see what we get. Maybe we also find out that some noisy vehicles are also the highest polluting vehicles. Now we are doing, actually today we are starting some sensors and IT integration in Austria, tolling systems, real-time technical info retrieval, things like this. Then we will go back to Rotterdam in a city center location. In June, we have a campaign in Florence, low emission zone. And in autumn, we will measure in multi-lane highways in Planec and Madrid. And we will even measure also ship and rail noise and emissions in Valencia. So as you can see, a lot of things happening. And here is an example of how multi-lane measurement could be done as well. And that's it. Thank you very much.
Thank you very much. Don't worry. Okay. The last noise radar prototype to review is the MEDUS technology and the hydro noise radar prototype, and developed in France. We welcome Mr. David Bernfield and Mr. Christopher Mietlicki, inventor of the device. Please tell us about it.
Okay.
Thank you.
Can you share the slide, please? Thank you very much. So, hello everybody. So I will present an update on Medusa technology, which is a system which is already 3 years old, and then I will talk about Hydra prototype, which is a real noise radar for finding drivers. Next slide, please. So just a little slide to explain that we are working with multiple microphone systems since 2010. First experience was about the noise, the aircraft noise detection. We started with a Japanese system, which was very precise and very interesting. And we were convinced since this epoch that it was a very good technology that we can apply to many other contexts. So we developed a generic system, generic purpose system, which name is Medusa. Can you change the slide, please? So Medusa is this system. It's a 4 microphone system. The 4 microphones are on a tetrahedron, and on in the center of the tetrahedron, there is also an imaging system that can take pictures at 360 degrees. And the capacity of the system is to map the noise direction directly in the image, which is very interesting. Here are an example of some bikes that are passing in front of Medusa. And as you see, if we zoom on the noise peak, then we have the typical angle signature with 2 angles, azimuth angle and elevation angle. That was my colleague from Switzerland already showed a thing like this. It is the typical angle signature of vehicle passing in front of the system. Next slide, please. So as you see, of course, here we have 3 peaks. And for these 3 peaks, we detect the passage of every vehicle. Next slide. And it is something that can be generalized. Here you see, if you only look at the noise level, it is absolutely impossible to count the number of vehicles that were passing in front of the system during this interval of time. And if you look at the angles, things seems obvious. So it is a very interesting technology to combine to classical noise level measurement, or even noise texture, noise analysis. Next slide, please. So we used Medusa to develop an educational noise system where we detect the vehicles that are passing from left to right or from right to left in front of the system. And we calculate the noise level. And if the noise level is above a certain threshold, then we power on a panel, a display panel, with a message indicating that the vehicle makes too much noise. And we have 2 panels in each direction. Of course, this system only works when it is a vehicle, and not when it is a dog or a plane or something else. Medusa can also be used for other applications or other use case, like this one, for example. Here we see clearly something which travels in the sky. So clearly it's not a dog, it's not a car also. And so it is a very convenient way to classify the events. And it is very more precise than analyzing the frequencies and the spectrum of the noise to classify the kind of event it is. Next slide, please. Just to finish with Medusa, Medusa is also used, for example, here to manage the noise in some streets in Paris. For example, here with 3 bars, and here we get the noise coming from the 3 terraces in front of the bars, and we drive some light indicators in each bar in order to give a feedback to the bar holder and to encourage self-regulation. Next slide, please. So this was Medusa, and we were asked by the French government to use that technology to develop a noise radar in order to find vehicles. So we developed Hydra system, which is this one. It's still a prototype, but as you see, it is something very close to a final product. So the idea of the system is to combine 2 Medusa. Can you change the slide, please? So here is a little schema of the system. So you have 2 Medusa system which are installed on the top and on the bottom of the radar. Then we also install 2 automatic license plate recognition cameras in each direction and a wide-angle camera in order to get the whole scene of the vehicle passing in front of the system. So next slide, how it works. In fact, the direction of arrival of the main noise source is calculated every 25 times per second. And so the 2 acoustic systems evaluate the direction of arrival, and to be valid, a measurement requires that the 2 acoustic system focuses simultaneously on the same source. So it's a very strong way to filter the data and to avoid the situation where there are many sources in competition. So it is something that works really well. And using this data, we track the noisiest acoustic source over its entire path in front of the system. Then we couple this with a video recorded by the wide-angle camera, and we make a kind of matching between acoustics and imaging data in order to keep only the measurements that we can surely affect. We can only surely how to say, les affecter sur un véhicule.
That we can link to a particular vehicle.
Yes, yes, we only keep the measurement we can link to the vehicle that is tracked. Next slide, please. There are 2 big challenges in order to solve for this system. First challenge is to measure the distance. Why do we have to do this? Next slide, please. The problem is that if we only measure the noise with a sound level meter, we don't know at which distance is the vehicle. And for example, if there are 2 lanes or 3 lanes, the system won't be fair because the car or the motorbike that will pass on the closest lane will have a kind of penalty due to the geometry, and it is not fair. So it's absolutely mandatory in our mind to estimate correctly the distance of the noisiest acoustic source. So it is the strongest challenge we had to solve, and that's why we decided to design Hydra using two acoustic systems and to focus two beams, acoustic beams on the source, in order to have the exact position of the source. It is something very important, because if the drivers know that, for example, they have to drive as far as possible from the system, they can have dangerous behavior. For example, driving in the wrong sense in order to be on the further lane. So it is absolutely mandatory to be fair. Next slide, please. So the other challenge has already been explained a little bit by my colleague from Switzerland. The question is how to isolate the noise of a vehicle when there are many vehicles. Because if we build a noise radar that is only able to give fine for vehicles when there is only one lane and one vehicle passing in front of the system and no other noise, the efficacy of the system will be very bad. So I have some slides to show you now. It is a situation, next slide please. It's a situation that is a little bit complex but completely realistic. So it's a computer simulation. So here is a situation where we install a system in front of a 3-lane road, and then I simulate a passage of a motorbike, which is the green one. And if we put a sound level meter, it is the kind of shape of plot we will detect. Then we will add some other vehicles. Please, can you change slides? So second vehicle, and 3 vehicle again, so you can change the slide again, please, and again. So yes, so 5 vehicles are passing. If they were isolated, you will have the kind of colored plot you see. And next slide, please. If you put a sound level meter in front of that situation, here is the kind of global level shape you will have. So it's absolutely impossible to see that you have 5 vehicles. And the level is, of course, a kind of sum of the individual noise level of every vehicle. Next slide, please. If you put a Medusa system, then using the angles, the blue angle is the azimuth angle, and the green angle is the elevation one. If you look at the blue angle, then you can see that there are 3 vehicles that will be the noisiest one at a certain moment. For example, the green one, the green motorbike, then the light blue motorbike, then the blue motorbike will be the noisiest vehicle at a certain moment. But if we take the level measured by the sound level meter, it's the black one. You see that we have an offset, which is due to the complexity of the scene, and the level that you will keep as the maximum level of every vehicle will be wrong, particularly for a light blue motorbike, because at that moment there are 3 or 4 vehicles that are cumulated, and so the global level, the global noise level measured by a sound level meter will be wrong. So to avoid this, we used a kind of acoustic signal treatment, like a sort of beamforming. And then next slide, please. What you see is the result of that treatment, and it shows that even in a complex situation, we can measure precisely the level of the noisiest source. So that is what we implemented in the Hydra system in order to find vehicles, even if they are not only one in front of the system. Next slide, please. I have a little video. Maybe you can switch the computer on that, or maybe if you click. Yes, thank you very much. So you see here, it's a little video of the Hydra system, which is working really. And you see that the motorbike is passing in front of the system. There is a vehicle recognition with a box, and we are able to put the acoustic beam of the motorbike in the image, and we match the two information, and it is the condition we use in order to keep a measurement as valid. So here is an example of a motorbike with
I'm sorry,
yeah.
but we're running out of time.
Yeah, just
you will need to
just
wrap up the
30
presentation.
seconds.
Yeah, thanks.
30 seconds. I finish. Can you change the slide, please? Okay, so here are typical situations we had in real conditions. Next slide, please. And so we combine it with automatic number plate recognition cameras. So here is the complete characterized situation. So here is where we are now, and we are in the process of testing that system in France that year in order to get the type approval and start to implement it next year. Thank you very much, and sorry for being long.
Thank you.